Alright, anyways, so today's lecture is going to be all about creating computers in Redstone, but we won't be making a computer today. We'll just be going over a brief introduction on how they could be made. So, to understand how this is going to work, we first need to know about binary, which is basically a number system. Like, there are many number systems. The one that you're most familiar with would be decimal, which is base 10, which means that you've got the digits 0 to 9 before you create a new digit with like a 1 and a 0 for like the first bit. So that is basically like what a base 10 system would be. So what a base 2 system would be is instead of 0 to 9, you'd only have two numbers, 0 and 1. So what this means is that once you count up to 1, if you want to count an additional number after that, you'd have to add a 0 to the end. So it goes 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, and so on. So it's just like counting up in decimal, except that you have to add digits sooner. So the reason this is useful is because in computers, there are only two states for any circuit thing, like there's on and there's off. So we can actually represent on with the number 1 and off with the number 0. And that's how the computer understands all the logic. Anyways, so speaking about logic, the basis of logic in computers as well as Redstone is that we use these things called logic gates. So here are all of the basic logic gates, and let's just go over all of them. So the first one we have is the OR gate, which is pretty simple. There are two inputs. There's A and there's B. And if you turn on A or B, then the output turns on. So as you can see, it doesn't matter which one of them you turn on, as long as one of them is on. So this or that. Now, the second logic gate we have is the inverter, or the NOT gate. So this takes any signal, and it turns it from 0 to 1, or 1 to 0. In Minecraft, this is as simple as using a redstone torch. And that's actually going to be what we'll use to invert our signals in like 90% of circumstances. Okay, so now to combine these two basic things into some more advanced logic, the first thing we have here is the NAND gate, which is a combination of two NOTs and an OR. And what you end up getting is a circuit which only turns off when both inputs are on. So it has to be A and B, then it turns off. You might be thinking it's more useful to have it such that it turns on when A and B are on. So that's what the AND gate here is. So this lamp over here is going to turn on only when A and B are on. And this is actually identical to the NAND gate. The only difference is that you've got an extra torch on the end. So the N in NAND stands for NOT. So it's NOT AND, which means it's an inverted AND. And basically that just means put a torch on the output, invert the output, and that's what it is. So no, because the NAND gate is on by default. It only turns off when both inputs are like on. So it's sort of like the inverse of an OR gate. So the OR gate only turns on, is only off when both are off. The NAND is only off when both are on. Yeah. So anyways, the last one we have is the NOR gate, which is basically turn on any of the inputs and the output will turn off. Okay, that's all the basics. So the last two are actually going to be the most useful for computing right now. So here we have what's called an XOR. If you remember the OR gate from earlier, which turned on when either A or B were on, like, the difference here is that it's an XOR, which stands for exclusive OR. And it's exclusive because it needs to be A or B, but not both. It has to be specifically A or B. So it turns on when you turn one of them on, but you turn both of them on, it turns off. No, when both are off, it's off. When both are on, it's off. When only one of them are on, it's on. And the XNOR is basically just that with, like, inverted output, i.e. a torch on the end. So if you want to know how the XOR gate works, because it's sort of hard to see it when it's in this form, which is, like, sort of, like, squished together, but, like, this is the basic logic for it. So you've got this double inverter going across this line, and so a double inverter is just the same as the original output. So there. It's literally just the same as having an input just going straight through. But the way the XOR here works is that you've got an additional, like, AND gate in the middle. So what happens is when both inputs are on, then the AND gate turns on. And when the AND gate turns on, it basically floods, like, this line over here, as well as this line over here, which prevents them from turning off. And if they can't turn off, then these two torches at the front can't turn on. If that makes any sense. Mm-hmm. Correct. Because when the AND gate isn't on, it's just a double inverter. And a double inverter is the same as just sending the output straight through. Mm-hmm. Yeah, so that's how the XOR works. But I guess what's going to be more interesting is how we can actually use this property. So let's talk about addition. So just like with decimal or any other number system, you can actually add numbers together. So let's do that. Let's take the numbers, 10. In binary, that would be 1, 0, 1, 0. And you know this because, like, the first digit is 1, right? Same as in decimal. But the next digit is going to be worth 2. In decimal, like, it's going to be worth 10, because 10 is the order of magnitude in decimal. But since binary is base 2, it's going to be multiplied by 2 every time. So this is worth 2, this is worth 4, and this is worth 8. 8 plus 2 is 10. Correct. So yeah, and then 32 and 64 4, and so on. So anyways, let's try adding this 10 to something else. Anyone have any suggestions for numbers like 15 or like below? 15 or below. All right, whatever, fine. I'll just shift this up. Just add another bit. So 21, right? Let's see. So we'll start from 16 plus 5. So there. Wait, no. There. That's 10 plus 21. Actually, this is going to be really easy. So let's just add these together. So the first bit is 0 plus 1. And 0 plus 1 is going to be 1. The next bit is 1 plus 0, which is going to be 1, and so on. So actually, this was a really bad pick, because we're literally just adding 0 and 1 together. But let's make this a bit more interesting. Let's actually add... Yeah, let's add this. This is the number 5. No, 6 in binary. So what's going to happen now is the first bit is going to be 0 plus 0, which is 0. The second bit here is 1 plus 1. And now this is where we have to do some additional logic, because 1 plus 1 is going to give us 0, but it's going to give a little carry signal to the next bit. Just like in standard addition in maths, like you always have to carry over to the next digit if you're adding more than a single digit can hold. So now it's 1 plus 0 plus 1, which is again going to carry over. Now it's 1 plus 1 plus 0, which is again going to carry over. Finally, 1 plus 0 plus 0 is 1. So let's just verify that this is correct. So it's 10 plus 6. Should be 16, right? And it is, because 1, 2, 4, 8, 16. So far, so good. Sweet. Okay, so that's addition. Now, it's sort of tedious to have to do additions yourself, so why don't we try and automate this process? Let's get our computer to do it for us. So the thing is that in binary, the addition process is really simple. You can think about it as like, for two like single digit numbers, like let's say 0 and 0. You add them together, that's 0, right? So let's try and like imagine what kind of logic gate we could design for this. So the starting inputs, the inputs 0 and 0 will give the output 0. The inputs 0 and 1, or 1 and 0, it doesn't matter. But either way, it's going to give a 1. But if you add 1 and 1 together, you're going to get 1, 0. That's for a single bit. All right, let's actually ignore this carry bit over here and only focus on the rightmost bit. So let's observe what happens. When both inputs are off, the output is off. When one input is on, the output is on. And it doesn't matter which input is on. But the moment you turn on both inputs, the output goes back to being off. So can anyone tell me which logic gate this is? So it's only on when only a single input is on. As long as... Yeah, it's an XOR. So let's just build our XOR. We'll get into that. Okay, so let's just check that it behaves as expected. So both inputs are off. It's off. Let's add a 1, and that's a 1. Let's add another 1, and it should shift over to the next bit, or carry over, rather. Okay, so now we need to figure out our carry logic. So we know that the output only carries over when we're adding a 1 and a 1. What that means is there's only a carry when both input A and input B are on. So it has to be A and B. Which logic gate is that? Correct. So actually, very conveniently, the XOR gate that we're using has an AND gate inbuilt. So this torch over here is the AND gate. If you remember the stretched out logic from earlier, like, that AND gate is now here. So we can actually take this out to the side. Because this dust, which is powering the AND gate, is also powering this block. So I'll just put a torch out to the side and just bring that down. And there we go. So if we've understood everything correctly, this should, theoretically, add two numbers together. So let's give it a try. So 0 plus 1 is 1. 1 plus 0 is 1. Finally, 1 plus 1 is 1, 0, which is 2 in binary. So this is working so far, but it's only for one digit. So sort of boring. Let's move on. Let's try and find a way to get this to support more numbers than just, or more digits than just that one. So starting from our XOR gate, because that's like a good basis to start from. We're going to want to put another XOR gate to the side, another of what we call a half adder. And you'll see why what we built earlier is called a half adder. So we've got blah. If we have like two of these addition machines, we'll want to find a way to connect them up somehow so that the carry of the first one goes into the second one, which goes into the third one, and so on. So actually what we could do is we could simply just make another XOR gate. So I'm going to do that. So the XOR gate here is basically going to, like, all right, so the first stage of the input here is we add together, like, these two inputs, the ones on the digit itself. The next XOR gate is going to take the output of that result, and it's going to add it with the carry of the one, of, like, the XOR which came before. So, like, this right here, this is going to be a carry signal. I'm just going to finish building this out. It'll hopefully become clear in a moment. My Discord is going crazy, one sec. It's gonna be really annoying on the recording. Right, there, do not disturb. Okay, anyways, so Here, I've got 2 more XORs connected. Now let's just see what happens if... I'm just going to change this a little bit. Okay, so I'm going to take this torch over here and basically feed it into this XOR right here. Now theoretically, this should take the carry of this bit and bring it over to this XOR and add it to that. And I'm just going to take the AND off the side here. No, actually, this is a single bit. It's probably hard to see because, like, they're on the same level. But basically, each one of these XOR units is an individual digit. Yeah, actually, good idea. So I'll just do that. Mm-hmm. Yep. Oh yeah, true. I was just sort of using them to signify, like, each digit, but good idea. Actually, since we have 2 shades of each, I could just do this. Okay, so now we can differentiate between... Oh, except we do want them to be, like, unified, right? Yeah, actually, I'm just going to change it up one more time. All right, there. Hopefully now it should be clear which one is the first number and which one is the second. So let's just give this thing a spin. Let's try adding 1. Or 1, 1, which is free. So that's going to be free. So, like, if we don't actually do any addition, this works just fine. But now let's try adding another 1 as the second number. And what happens is that it carries over. So this free basically, like, generates a carry signal here, which goes into the next XOR here, which generates another carry signal, which goes out here. And for some reason, this bit is on. Oh, wait, right, okay, so I needed another torch here. Yeah, all right, that's fixed now. Okay, so there's actually one last thing that we need to do, which is we need to get a carry signal from this XOR over here. Because, like, this carry signal here also needs to be accounted for. There's basically 2 places where a carry could be generated, which is a carry which is first generated, like, by adding a 1 and a 1 together, and, like, the carry which is generated from adding the carry of the last digit. So this one right here. So when I build the next XOR over here, I'm going to just make a little bit of a modification to support this signal. So I'm going to take, like, the carry of this one just the same. But now I'm going to also add a little wire from this carry over here so that it can connect with this and also go to that XOR. Right. Now let's just build more units. Actually, I'm going to world edit this. Yeah. One sec. All right, so let's just connect up all of these XORs the same way we did for this. So we'll take the carry from here, and we'll take the carry from here, and we'll bring it down to the next level down here. We'll do the same for the next one. And finally, actually, this XOR isn't necessary. So we do have like one carry out bit over here. It's not actually a remainder. It's sort of like, because if you add like, imagine in decimal, if you add two single-digit numbers together, like the biggest result that you can get is 2 bits, right? It's always going to be one more digit than like the maximum size. So since we have like 4 digits here, there's going to be like a maximum of 5 digits for addition. And yeah, so theoretically this should be working. So I'm just gonna give this a spin. Someone tell me 2 numbers to add together. All right, so we'll do 3 for the line wool, and 5. 3 is like 1, 1. 5 is 1, 0, 1. So the result is 8, which is actually what we wanted. So let's just see what's happening here. So in the first bit, we're adding 1 and 1, and that generates a carry signal. And on the second bit, we're adding just a single 1, but that 1 adds with the carry signal, and so it produces another carry signal here, which goes to the next bit. And on the next bit, it's also a 0, 1. So like, it's going to add with that 1 and generate another carry signal, which finally gets added with 2 zeros. And so the output is just a single 1 on this last bit. So yeah, we've actually made a machine which can do the adding for us. But there's more. What if we want the machine to also subtract for us? Oh boy. No, we don't actually have to make any modifications to this adder. We can actually use this exact same hardware to also subtract. And the way we're going to do this is with something pretty magical, and it's called 2's complement. So if you come over here, yeah, this. So back to our little drawing board over here. We'll take the same 2 numbers that we tried before. So that was 10 and 6. But instead of adding them together, we want to subtract the 6. So what 2's complement is it's a way of representing negative numbers in binary. And it's the way that basically every computer uses. And the reason they use it is because you don't have to make any modifications to the hardware. Like, you can just use the same addition hardware to perform subtraction, because of the way that 2's complement works. So when you want to convert any number into 2's complement, the first bit over here will no longer be used to represent a value. Instead, it's going to be the sign. And what that means is that if it's a 0, that means it's a positive number. And if it's a 1, that means it's a negative number. So yeah, what was I saying? Okay, so negative, positive. But actually what that means is that since we're losing a bit here, and the bit is the leftmost bit, that means that the number of values you can represent in the positive range is halved. But that means you also like get that same number of negative values. So actually, the thing about like using this as a sign bit is that you could just say that this is the sign, and the remaining 4 digits here are the value of like how negative it is, right? The way computers actually do it is by inverting all of these first. So instead of 011, it's 1001. But there's also a problem with doing just that, which is now you've got this like value here, which is 10000, which is negative 0. Yeah, it's negative 0. No, this is a hardware thing. Alright, anyways, like I was saying, so like this negative 0 is basically like a waste of a single number, which actually, to be fair, isn't really a big deal in like any modern computer, because like that's like 1 in several billion numbers. But like we're gonna use, like this is actually called 1's complement, right? What we're gonna use is called 2's complement, where after inverting, we're gonna add a 1 to that inverted number. So we went from 0110 to 1001. And finally, we're going to add a 1 to this number, and what we'll get is 1010. So our final 2's complement version is 11010. That's negative 6. So far, so good. Does anyone have any questions right now? Because 2's complement is sort of a tricky one to wrap your head around. Actually, just forget the negative 0. Like, it's not that important. Like, right, let's go for it together. So this is 10 plus minus 6. So 0 plus 0 is 0. 1 plus 1 is 0, but carry over. 1 plus 0 plus 0 is 1. 1 plus 1 is 0, but carry over. And 1 plus 0 plus 1 is going to be 0, but it carries over. So it does carry over to, like, the carry out, but that doesn't matter because the carry out gets ignored. So anyways, 4, yes. 10 minus 6 is 4. And the sign bit is off, which means it's positive 4. Isn't it magical? Mm-hmm. Yeah. So you want to understand how 2's complement works, right? Without changing the hardware. Now, like, you want to understand how this actually works. But, like, the computer doesn't know that this is a negative number. To the computer, both of these are just numbers. Like, it doesn't know whether it's positive or negative. Like, it's up to your program to properly, like, determine all of that. Yeah, exactly. So, if you want to understand how 2's complement works, it's probably outside of the scope of what we're doing here today, but maybe ask it as a question after the next bit is done. Anyways, let's do the same thing here with our adder. So instead of adding 5 and 3, we're going to instead subtract 3 from 5. So we'll put in our 5 as per usual, 1, 0, 1. But now instead of putting in 1, 1 for our dark green wool, we're going to first convert it to -3. So what's 0, 0, 1, 1 in 2's complement? So the first step is to invert it, right? And then the next step is to add a 1 to that inverted number. So 1, 1, 0, 1. Yeah, that's our -3. So let's see what our output is. We actually get 2, as expected. And this carry bit is on, but we ignore this. I'm actually just going to get rid of this lamp. So yeah, that is the only part of the number that you need to care about. This is what they do. Yeah, probably. Two 4-bit numbers. Yeah, that's beyond today. But for multiplication, you'd need either, for a multiplier, you either need multiple adders, like, which is known as a combinational multiplier, or you can simply use a single adder but loop the input back in on itself, like, which is just using a clock. I'll actually go over that very briefly after we're done with this last thing here. So instead of converting the numbers to negative ourselves, what if we actually install a little thing here, which will handle the conversion for us? So why don't we create a little thing to invert the number for us? And we'll do it for our second number, the dark green wool. So I'm just going to try and build a conditional NOT gate, if I can remember how to do it. I'm just gonna Google it real quick, because it's slipping my mind. Yep. Yeah. Sort of. I'm not sure. Okay, what I actually have here is a conditional NOT gate. So what's going to happen is we're going to send a signal on the top to all of these little units to tell them to invert, right? So when we turn this on, that inverts the signal, and we can just play around with the bottom just fine. But actually, guess what? This can be known as another name. So rather than conditional inverter, what if I simply called it an XOR gate? XORs are powerful devices. Because that's literally like XOR gates are conditional inverters. That's logically like what they're doing. Yeah, I'm just gonna build this on all the others. Or rather, I'm gonna just world edit them in. Okay, so now the last step is to put all these together. Or not the last step, the second last. So now we've got this little thing here to invert the all the inputs of the second input thing. Or wait, hold on. I missed one thing. Yeah. Yeah, that's what it's doing. Okay, so this lever here will invert our inputs for the second number. As you can see, it's done that just fine. But there's one last step, which is we also need to add a 1. And, well, guess what? This thing here, this lever, which previously had no use, well, now it's got a use. So this is called the carry-in. Yeah, this lever here is called the carry-in, and it's used for subtraction among a few other things, which I won't cover. So I'm just going to bring this signal out. Hey, there we go. Yeah, so this is actually now inverting and adding 1, because the carry-in adds 1. So, as expected, when you do -0, right? Like, I mean, when you turn 0 negative, like it should just be 0, and our output reflects that. And now we can just do our subtraction without having to worry about the conversion. So let's do 1, 1, so that's 3. And actually this time, instead of like doing 5 minus 3, let's do 3 minus 5. So 3 minus 101. And the output should be -2, which this number here, 1110, if we subtract 1. So we're going to do the same steps to convert it, but in reverse. So subtract 1, so that's 1101. Now invert it, so 0010. So it is indeed -2. Oh yeah. Yeah, wait, you could. Or could you? I'm not sure. Okay, yeah, you can then. Cool. That's something I didn't know. Alright, that's actually all the material that I was planning to cover today. But since you all asked some interesting questions, let's go over binary multiplication. Yeah. So someone give me 2 numbers, preferably 2 small numbers. Because, like, we're going to end up with a big result. 2 and 3. Let's do it. Okay, so 2, 3. So the way multiplication works is pretty simple. What we do is we take the first number, and we're going to basically do a lot of additions. And the second number tells us exactly what additions we need to do and where. So first of all, we take 2, we'll multiply it by 1, right? So that's going to be just 2. Now we're going to take this 2 here, and we're going to multiply it, or no, we're going to add it at this bit instead. So 1 bit up. Now the next thing is we're going to, well, now this bit is a 0, so we're not going to add anything. We're just going to do 0, right? And then the last bit is also going to just be another 0, and we've run out of space. I didn't build this for multiplication. But anyways, so what's going to happen then is we're basically just adding these 2 numbers together, and the final output should be 110, which is actually 6, right? Because 2 plus 4 is 6. So the first number is the one that is getting added every time. And the second number, like, you look at each individual bit. So the first bit, if it's a 1, then you add the first number. Or if it's a 0, then you don't add anything. Then you shift to the next digit. And when you shift to the next digit, you also shift the first number. So instead of 2, it's actually going to become 4. Because if you shift it to the side, you're multiplying it by 2. That's how it works. Because 2 plus 4 is 6. Is everyone understanding all this? So the way that you would actually create a multiplier in Minecraft, or even in the real world, is that you would take, like, an adder, and most of them will do it using a clock. So they would have, like, the first number in a shift register, and every time, like, you add it, you're gonna also shift it, right? And the second number is simply used for logic, and it's gonna take every single bit and check if it's a 1 or a 0. If it's a 1, it's going to add the number in the shift register. If it's a 0, it's going to skip and just do nothing. Cool. Does anyone have any other questions? Yeah, this is the basics of binary. And, or not the basics of binary, but rather the basics of, like, computing. Because this is only, like, keep in mind, this is only the thing which does the math. Right? Like, and there's so much more that goes into a computer. Like, you actually need the control, like, signals and stuff. Decimal to binary. Yeah. Mm. Mm-hmm. Yeah, I've actually made some converters, like, um, yeah. Mm-hmm. Yeah.